And next we have Cadet Naomi Edegbe. She's going to talk about looking for defects in munitions.
Good afternoon, I'm Naomi Edegbe, and I'll be presenting to you my capstone on munitions. So to start, let me orient you to our photos. On the left is a picture of a manufacturing plant from World War I. In World War I, during the Great War, the nature of war fighting changed. So while small arms fire could meet the need for close armed combat, the necessity of big guns or munitions, larger munitions, due to trench warfare, created to you that we have used munitions at some point in our summer training. It has applicable use in field artillery, air defense, and the engineer corps, and munitions have a great use and capability for protecting our soldiers on the ground. So what if munitions that are supposed to look like this and look like this in current scanning? On the top left is a picture of munition during World War I. It's not produced anymore, but how it used to occur is that in these manufacturing plants, workers would by hand very closely assemble these munitions, their fuses, check for components, and go through a rigorous inspection process. With humans, more often than not, at some point there comes a mistake. So what these mistakes would look like would be duds. The duds, either the fuse would move and the munition would become basically a live fire, and these munitions may go off as an explosive in the weapon system or closely thereafter, right before employment. So these duds basically meant that there was defects in the munition process. Today, on the top right, these are the munitions that X-ray technicians or radiographers can scan for. And upon a filter, they'll assess the image as such. So when images look like this in X-ray scanning, sometimes they can report like this. In these two images, upon initial inspection, they were actually accepted by radiographers for deployable use. Upon closer inspection, you can see on the left that there is a large crack in the munition, and on the right that there is piping and porosity in the munition, indicating that there might be small air bubbles or X, Y, and Z that would report as defects. This creates our problem set. Defects in high explosive main shell and shell interiors may cause catastrophic effects if employed. And the objective is to use a computational process that assesses munitions with feature extraction. So what the current manufacturing process looks like is from an armament center, the X-rays are collected, and if you follow the green, a human in the loop or radiographers assess very closely in a dark room thousands of images to classify whether or not they're able to be used. What this project suggests is implementing a convolutional neural network learning detection in order to help assist the radiographers in the process for checking. So instead of from the X-ray image collection, there's a data creation process that makes the X-ray images readable for our code. The CNN learning prediction is two-order in effect. The first order is anomaly detector, which basically means that we classify in a binary form, is this a defect or is it not? And the second order is a feature extractor, which basically characterizes the defects in munitions and labels them. The third order would be, at this classification period, reintegrating the radiographers for a secondary check and finally deploying them. I'm implementing this project through computer vision. So computer vision is an image analysis technique. Right now in image analysis, you've already identified that I'm a human. This is a presentation. It's very easy for us learning through that process. It's not that easy for computers to do it. So what object detection does is it takes the image and places a bounding box, and semantic segmentation places a filter on recognized objects in images. What this will apply is for feature extractions, we're able to highlight features, and for object detection, we're able to label and classify them. The data I received is about 80,000 annotated images. On the right, I'd like to point out that the original input image, although there's a difference in grayscale, is actually the entire main fill. So when it's read through a filter, it actually looks like the image further on the right, which in this assembly of data is around 600 gigabytes of untar data. The images were quite large, so it takes a while for them to run through a computer, but out of the 80,000 images, only 350 were rejected. And for the casting features that were applied, these are things that I can train the CNN algorithm to learn for. When I formed the data, I took a creation summary from the radiographers and basically matched the labels to create a final test set. This final test set lost about 2,000 images. Either images were missing or they were labeled twice. And the defects reduced down from 350 images to about 245. So when we receive the images, we send them through a pre-processing. It was 4-step in nature. The first step was taking the input image. The second step was applying a Wallace filter to magnify the black and white pixels in the image. And the third step was to do edge detection. So that's what you see in the green. And the final step is to cut the unnecessary background data. And then I just added and resized the images into an aspect ratio where I wouldn't lose data, but it was going to be readable for my CNN. And then I ran them through an autoencoder. So what an autoencoder does is it encodes and compresses an image into a readable format of code. And when it decompresses, it's reconstructing the image. So through all of these images I'm running through the autoencoder, it's learning how to detect and analyze features and noise that should be recognizable as an acceptable image. Therefore, a reconstruction threshold is averaged throughout my data. What happens with the reconstruction threshold now is when I introduce a defect, the reconstruction error of that munition is higher. This flags my munition as a defect, so that does the anomaly detection. Where I'm currently at in this process is the autoencoder works and the reconstruction occurs. But from the pre-processing and the edge detection, there's quite a bit of images where the edge detection is missing. So what happens is that I highlighted the part where the edges are either cut off too early or like within the munition. So what that basically means is that when I'm doing my reconstruction error for the threshold, it may just be too high adjusted to automatically flag like more of the munitions that are running through the system that have defects. And therefore, right now, for conclusions and work done, the annotations were matched. The Wallace filter was applied for pre-processing, and the edge detection was done so I could run it through an algorithm. The autoencoder reconstruction, I have a threshold. The future movements for this project would be looking back at the pre-processing and trying to refine it a bit more, and then moving forward again, just performing the object detection on features with like other CNN techniques. Pending any questions, this concludes my brief.